Welcome back. In this video, you'll learn how to represent a function as a power series by using differentiation and integration. Let's get to it. All right, so previously we have seen that a power series can be used to represent a function that is in a form similar to the sum of a geometric series. However, we can also represent functions that are the derivative and antiderivative of functions similar to that form. All right, so just as a refresher, remember that this is the form of a geometric series, the sum from n equals 0 to infinity of some constant a times the common ratio r to the power of n. And a geometric series converges when the absolute value of r is less than 1. And when a geometric series converges, it will have a sum that can be represented by a divided by 1 minus r. All right, and so what we have seen in previous videos is that we can take a function that is similar to this form, such as 1 divided by 1 minus x, and rewrite that as a power series, or you could view it as a geometric power series, right? So in this case, 1 would be equal to a, and x would be equal to r. And so the geometric power series would be 1 times x to the power of n. And this power series converges when the absolute value of x is less than 1. All right, and so that's what we've been doing in the past. We have been taking functions that are similar to this form of the sum of a geometric series and manipulating them algebraically into that form so that we can rewrite them as a geometric power series. But we've only looked at how to do that for functions that were similar to that form. But what we're going to do now is look at how to represent a function that is either the derivative or the antiderivative of a function of that form. For example, consider this function. We have f of x is equal to the natural log of 1 plus x. This function doesn't look anything like a divided by 1 minus r or 1 divided by 1 minus x, right? It's the natural log of 1 plus x. It's a completely different function. But watch what happens if we take the derivative of this function. F prime of x is equal to the derivative of the natural log of 1 plus x. The derivative of a natural log function will be 1 divided by the inside function times the derivative of that inside function, right? So we're going to have 1 divided by 1 plus x, and then we're going to multiply by the derivative of 1 plus x, but the derivative of 1 is 0, and the derivative of x is 1, so we'd just be multiplying by 1. And so the derivative, f prime of x, of this function is 1 divided by 1 plus x. And this is in a very similar form to a divided by 1 minus r, right? This looks very close to the sum of a geometric series. So what we could do in this case is represent the derivative of this function as a power series, and then integrate that power series to get back to the original function. And that resulting power series will represent this function. Right, so if we take the derivative of our function to get it in a form that is similar to the sum of a geometric series, we would have to integrate that function to get back to the original function. Okay, so that's one direction that we could go in, but what if we had a function that looked like this? What if we had f of x is equal to 1 divided by 1 plus x squared? This function is close to the form of the sum of a geometric series, but it's not quite there because we have a quantity squared in the denominator. But watch what happens if we were to integrate this function, right? If we integrate f of x dx, that will be equal to the integral of 1 plus x to the power of negative 2 dx. All right, I'm just moving this quantity to the numerator, which makes that exponent negative. And then what we could do here is use u substitution, right? We could set u equal to 1 plus x, and then a derivative du dx would be equal to 1 because the derivative of 1 is 0 and the derivative of x is 1. And so du is equal to dx, and so this is equal to the integral of u to the power of negative 2 times du. All right, and then we would use the power rule for integration. And so we would add 1 to this exponent to have u to the negative first power, and then we would divide by that new exponent of negative 1. So what we would have here is that this integral is equal to u to the negative first power divided by negative 1. But then you don't want to forget your constant of integration, so we need to add plus c. And then if we replace u with what we set it equal to, that's 1 plus x. So I'll rewrite u to the negative first power to be 1 plus x to the power of negative 1. And then we can move that back to the denominator and then move that negative up top. It doesn't matter where we place that negative. What matters is that this is a negative value. And so what this would be equal to is -1 divided by 1 plus x to the first power, right? If we move that to the denominator, that negative exponent becomes positive, all right? And then don't forget plus c. But what we find here is that the integral of this function is -1 divided by 1 plus x plus c. Now, if I rewrite that to look a little bit nicer, what we would have is -1 divided by 1 plus x plus c. Okay, and so the integral of this function is in a form that is similar to the sum of a geometric series, right? We have a constant divided by 1 plus x, but that can easily be changed to be 1 minus some common ratio. And so similar to this example, where the derivative of a function was in that form of the sum of a geometric series, the integral of this function is in a form similar to the sum of a geometric series. And so you're going to come across functions like these two, where integrating them or taking the derivative of them will give you a function that you can rewrite as a geometric power series. And doing so will then allow you to find a power series to represent the original functions by either integrating or taking the derivative of that power series, depending on what you did to your original function. Right, so in this first case where we took the derivative of the original function, once we express this derivative as a power series, we would need to integrate that power series to get back to the original function. We would not want to take the derivative again because that would be the second derivative. In the same way, since we integrated this function to get this function, once we represent this as a power series, we would then want to take the derivative of that power series to get back to the original function. Right? So this is the antiderivative of the function. And so if we represented that as a power series, that power series would be the antiderivative of this function. So we would need to differentiate that to get back to the original function. And that resulting power series would represent that function. Okay, so that's the big idea of what we're going to do in this video. We're going to take a look at each of these functions and show you how you can either differentiate or integrate a power series in order to represent a function whose derivative or antiderivative is similar to the sum of a geometric series. Okay, and so before we take a look at each of these functions and how we're going to represent them as power series, we need to quickly review the rules for differentiating and integrating a power series. Remember that if you have a power series in this form, which is the general form of a power series, you can easily differentiate or integrate it by just using the power rule for derivatives or the power rule for integration on the part that involves x, right? So if we take the derivative of a power series, we will multiply the exponent of that quantity down. So we have n times a sub n times this quantity, and then we subtract 1 from that exponent. Okay, so we multiply the exponent down and subtract 1 from the exponent. That's all you have to do to take the derivative of a power series. You leave everything else alone. Everything else that doesn't involve x, that you would classify as being a sub n, that is not going to change when you take the derivative of your power series. It's also not going to change when you take the integral of a power series. Once again, the only thing that's going to change or be affected by the integration process is that quantity of x minus c. In this case, the power rule of integration says that we add 1 to the exponent, so we have x minus c to the power of n plus 1, and then we divide by that new exponent of n plus 1. The only other thing you need to remember is that when you integrate a power series, you have to include that constant of integration, that plus c that you would have to write when you first learned about indefinite integrals. That's going to show up right here. Okay, so typically we write that on the outside of the power series because that's not added to every single term. We just add one constant of integration for the entire power series that represents the integral of the original power series. Okay, so those are our rules for differentiation and integration of a power series. But now let's take a look at each of these functions and how we could represent them as power series. And so let's start with this function, f of x is equal to the natural log of 1 plus x. All right, so here's our example written a little bit more formally. We want to find a power series for that function. F of x equals the natural log of 1 plus x, centered at 0, and we want to determine the interval of convergence for that power series. All right, so we'll talk about the interval of convergence once we find our power series, And so we'll come back to that later. For now, let's just focus on how we're going to express this function as a power series. All right, so remember that we found that the derivative of this function is 1 divided by 1 plus x, right? This is the derivative of the natural log of 1 plus x. And so since this is similar to the form of the sum of a geometric series, remember that is a divided by 1 minus r, we can rewrite this derivative as a geometric power series. Okay, the only thing that doesn't quite match up here is that we need to have 1 minus a common ratio, not 1 plus a common ratio. And so we can fix that pretty easily. We can just subtract negative x, and that would be the same as 1 plus x, right? We could rewrite this to be 1 divided by 1 minus negative x. Those two negatives would cancel out to become positive, and so this is an equivalent way to write this derivative. Okay, so now we can see that a is equal to 1 and r is equal to negative x, and so we can rewrite this derivative as a geometric power series, right? Remember that this sum of a geometric series is equal to a geometric series, which is the sum from n equals 0 to infinity of a times r to the power of n. So in this case, we'll have that our derivative is equal to the sum from n equals 0 to infinity of a, which is just 1, times r, which is negative x to the power of n. All right, now if we simplify, 1 times anything is just that value, so we can ignore that 1. But then I'm going to separate this negative from the x, and what I mean by that is we're going to have the sum from n equals 0 to infinity of negative 1 times x to the power of n, right? Negative 1 times x is the same as the negative x, so I just split that up. So now we can take each part to the power of n, and what we will have is the sum from n equals 0 to infinity of negative 1 to the power of n times x to the power of n. All right, and so this right here is the power series that represents the derivative of our original function. Okay, so if I clean up my work, we have now found that the derivative of our function is equal to 1 divided by 1 plus x, which can be represented as a power series where we have the sum from n equals 0 to infinity of negative 1 to the power of n times x to the power of n. Okay, so this power series represents the derivative of our function, but we want to find a power series that represents the original function. So what we have to do is integrate this power series, right? To get back from the derivative to the original function, we need to integrate the derivative. So what we're going to do is integrate f prime of x dx, and that is going to be equal to f of x, right? The derivative and the integral cancel each other out. And so f of x will be equal to the integral of this power series. So what we'll do is use the power rule for integration on our power series. We're going to add 1 to this exponent and then divide by that new exponent. All right, and don't forget that because we're integrating, we're going to have that constant of integration. And so we have c plus the sum from n equals 0 to infinity of negative 1 to the power of n times x to the power of n plus 1. We add 1 to the exponent and then divide by that new exponent of n plus 1. All right, we do not change this negative 1 to the power of n in any way. That does not involve x. We're only using the power rule for x to the power of n. All right, that is the only part that is affected by the integration process. And so what we have right here is a power series that represents the function f of x, the natural log of 1 plus x. That's what we wanted to do. The only thing we need to determine yet is this value of c. What is that equal to? And so the way we'll do that, first of all, remember that f of x is equal to this function. So we would say that the natural log of 1 plus x is equal to c plus the sum from n equals 0 to infinity of negative 1 to the power of n times x to the power of n plus 1 divided by n plus 1. And then what we can do is just pick a convenient value of x that when it is plugged in will allow us to solve for c. In this case, if we let x equal 0, right, if we say that x is equal to 0, this power series is just going to become 0, because 0 to the power of n plus 1 would just be 0, times negative 1 to the power of n would still be 0, divided by n plus 1 is still 0. So this whole sum would just become 0, and so if x equals 0, we will have the natural log of 1 plus 0 is equal to c plus 0. And a natural log of 1 plus 0 is the natural log of 1, and the natural log of 1 is equal to 0. And so what we'll have is that 0 is equal to c. And so that constant of integration in this case is just equal to 0. And so what we learn from all of this is that we can just completely remove that constant of integration, and what we'll have left over is a power series that represents our function f of x. All right, so since c is equal to 0, we will say that f of x, which is the natural log of 1 plus x, is equal to the sum from n equals 0 to infinity of negative 1 to the power of n times x to the power of n plus 1 divided by n plus 1. All right, so that is the power series centered at 0 that represents our original function. All right, and it's centered at 0 because we just have x raised to the power of n plus 1. We don't have x plus or minus some other constant. It's just x raised to that power. All right, so now that we found a power series to represent our function f of x, now what we want to do is determine the interval of convergence for that power series. And the way we're going to go about finding the interval of convergence is maybe a little bit different than you would have expected. What we're going to use is the fact that the radius and interval of convergence for a power series and its derivative and integral are all going to be the same, except the derivative or integral may gain or lose one or two endpoints for the interval of convergence. All right, so what's important to understand here is that we know how to find the interval of convergence for a geometric power series, right? The first power series that we wrote for the function that was similar to the sum of a geometric series. We know how to find the interval of convergence for that series by remembering that a geometric series converges when the absolute value of r is less than 1. So we can find the interval of convergence for that series, but we won't necessarily be able to do that as directly for the power series that represents our function, right? Because this power series may not necessarily be a geometric series. We can't use the same method that we would use for the power series that directly came from the sum of a geometric series. So what we'll do is find the interval of convergence for that power series that we got from the derivative of our function, and whatever that interval of convergence is, and the radius, they will be the exact same for our power series that we got by integrating it. The only thing that we have to check are the endpoints. The endpoints might be different. Okay, and so if you're not familiar with that concept, be sure to watch my video where I talk about how to differentiate and integrate power series. In that video, I go through and show you that the radius and interval of convergence will be the same for a power series and its derivative and integral, except for the endpoints. The endpoints of the interval of convergence may be different. And we're using that concept here in this problem to find the interval of convergence for the power series that represents our function whose derivative is similar to the sum of a geometric series. All right, so now let's work on actually finding that interval of convergence. So let's look at our geometric power series that came from our derivative. In this case, the common ratio r was negative x, or you could just use x, because either way, the absolute value of negative x is the absolute value of x, because the absolute value bars will eliminate that negative. So we would have the absolute value of x is less than 1. And what that tells us is two different things. The first thing is that our radius is equal to 1. That's one thing that tells us, right? Whenever you have the absolute value of x minus c less than some value, that value is the radius. In this case, c is 0 because our power series is centered at 0, and so we just have the absolute value of x is less than some value, which is 1, and so 1 is the radius. Okay, and so that's one thing that this tells us, but it also tells us that when x is between 1 and negative 1, this power series converges. All right, so the interval of convergence for this power series is from negative 1 to positive 1. All right, so that's our starting point. This is the interval of convergence for this power series, but remember, to find the power series that represents our function, we integrated this power series. And so this power series, the integral of this power series, may or may not also include the endpoints of that interval of convergence. We may need to change these endpoints from being excluded from the interval of convergence to being included with closed brackets. So all we have to do now is check those endpoints for this power series. Okay, the radius is going to be the same. The radius for this power series will be 1. That's not going to be any different. but we will need to check these endpoints for the interval of convergence. So if I clean up my work here, let's start by checking the first endpoint, -1. When x is equal to -1, our power series will look like this. We have the sum from n equals 0 to infinity of -1 to the power of n times -1 to the power of n plus 1 divided by n plus 1. Right, we just replaced this x with -1. And now we have -1 to the power of n and -1 to the power of n plus 1 in the numerator. So we can actually combine those exponents, right? Since we have the same base here of -1, we can add the exponents and just have -1 to the power of n plus 1. All right, so this will be equal to the sum from n equals 0 to infinity of -1 to the power of n plus 1 divided by n plus 1. Okay, we just added those exponents. But now we can simplify that a little bit. N plus n is 2n, so we'd have 2n plus 1. So I'm just going to rewrite that. The power of -1 will be 2n plus 1. And now something interesting is going to happen here. -1 raised to the power of 2n plus 1, that power is always going to be an odd value, right? If n is even, an even number times 2 is still even. And if n is an odd number times 2 will make it even. And so we're always going to have an even value plus 1, which makes it odd. So -1, no matter the value of n, will always be raised to a negative power, which always results in -1. So this -1 to the power of 2n plus 1 is just always -1 for all values of n. So we could rewrite this to be the sum from n equals 0 to infinity of -1 divided by n plus 1. And now we have a simplified series that we can test the convergence or divergence for. If it's convergent, then that means that our power series converges when x equals -1, so we would want to include that endpoint in the interval of convergence. But if this series diverges, we will leave that bracket open and not include -1 in the interval of convergence. Okay? And so how can we determine the convergence of this series right here? Well, the series that we have here is similar to a p-series, right? We have -1 divided by n to the first power plus 1. We could compare this series to a p-series and use one of our comparison tests. Specifically, I'm going to compare it to this series. We'll have the sum from n equals 0 to infinity of 1 divided by n. Right, since we have n to the first power in the denominator here, I'm going to compare this series to a p-series where we have 1 divided by n to the first power. And because that power of n is 1, this is a p-series that diverges. In fact, this is the harmonic series, which is always a divergent series. And so this series diverges. And so what we can do is use a comparison test to compare this series to this series, and hopefully we will be able to conclude that this series also diverges. All right, now in this case, I'm going to use the limit comparison test. And the limit comparison test allows us to do this. We will take the limit as n approaches infinity of the sequence from our original series divided by the sequence from our comparison series. And if that limit is equal to a finite value, then our series shares the same convergence or divergence as the comparison series. All right, so in this case, we're going to have -1 divided by n plus 1 divided by 1 divided by n. But dividing by a fraction is the same as multiplying by the reciprocal of that fraction. So instead of dividing this by 1 divided by n, we're going to multiply by n divided by 1 if we flip the numerator and denominator. So I'm going to erase this, and instead of dividing by 1 divided by n, we're going to multiply by n divided by 1. And this will be equal to the limit as n approaches infinity of -n divided by n plus 1. All right, n times -1 is -n, and 1 times n plus 1 is n plus 1. All right, now here we have a limit as n approaches infinity of a rational expression. And when that happens, what you can do is look at the highest power of n in the numerator and denominator. And if that power is equal, the limit as n approaches infinity of that expression will be equal to the ratio of the coefficients for the two terms with that highest power, right? So in this case, we have -n to the first power. That's the highest power of n in the numerator. And in the denominator, we have n to the first power as well. So the highest power of n in the numerator and denominator is the same. It's equal to 1. And so this limit as n approaches infinity will be equal to the ratio of the coefficients for those two terms. So we'll have -1, the coefficient of this term, divided by 1, the coefficient of this term. So this limit is equal to -1 divided by 1, which is just equal to -1. And so our limit is equal to -1, which is a finite value. It's not infinity or negative infinity, which means that our series diverges just like our comparison series. It will share that same divergence. All right, so now we have concluded that this series diverges, which means that when x equals -1, this power series is not a convergent series. So -1 will not be included in the interval of convergence. We will continue to exclude -1 by leaving this as an open bracket. Okay, so we're not going to make any changes to this interval of convergence just yet. We still need to check our other endpoint of +1. So if I clean up my work here, when x equals +1, our power series will look like this. We'll have the sum from n equals 0 to infinity of -1 to the power of n times 1 to the power of n plus 1 divided by n plus 1. Now 1 to the power of anything that's finite is just going to be 1. So we can rewrite this to be the sum from n equals 0 to infinity of -1 to the power of n divided by n plus 1, right? This 1 to the power of n plus 1 is just equal to 1, so we have 1 times the -1 to the power of n, which will just be -1 to the power of n. And so now what we have here is an alternating series, right? We have -1 to the power of n. That is going to make the terms of this series alternate between being positive and negative. And so what we can use to determine if this series converges or diverges is the alternating series test. All right, and so the alternating series test says that a series converges if it meets two requirements. The first requirement is that the limit as n approaches infinity of the sequence from the series must be equal to 0. And that sequence does not include the part of the series that makes it alternating. So we will exclude -1 to the power of n, and we'll just have 1 divided by n plus 1. All right, so we have 1 divided by n plus 1. Now, does the limit as n approaches infinity of this expression equal 0? Well, as n approaches infinity, n is getting larger and larger towards infinity, and so we have an increasing number plus 1 in the denominator, and so that denominator is increasingly getting larger, and so we have 1 divided by an increasing denominator, or 1 divided by infinity, which is always equal to 0. All right, and so the first requirement is met, and then the second requirement for the alternating series test is that our sequence is decreasing. In other words, a sub n plus 1 needs to be less than or equal to a sub n. The next term of the sequence needs to be less than or equal to the previous term. And so in this case, a sub n plus 1 will be 1 divided by n plus 1 plus 1, right? We're replacing this n with n plus 1. And so n plus 1 plus 1 would be n plus 2. So I'm just going to rewrite that to be n plus 2. So we have n plus 2, and that needs to be less than or equal to a sub n, which is 1 divided by n plus 1, right? A sub n is just our sequence. Okay, and so is 1 divided by n plus 2 less than or equal to 1 divided by n plus 1? Well, notice that the numerators are the same, so the only thing that's going to affect their values is the denominator, and we have n plus 2 compared to n plus 1. So this denominator will always be 1 greater than this denominator, right? We're adding 2 to the value of n as opposed to adding just 1 to the value of n. And when your fraction has a bigger denominator, the value of that fraction is smaller. So this fraction will always be less than or possibly equal to this expression. A sub n plus 1 is less than or equal to a sub n. So our second requirement is met, which means that this series is a convergent series. All right, so this series converges, which means that +1 should be included in the interval of convergence. So I'm going to change that open bracket to be a closed bracket. And now we have the interval of convergence for the power series that represents this function. Okay, so finally, we have completed this example. We have found a power series to represent our function, whose derivative is similar to the sum of a geometric series, and we found the radius and interval of convergence. Okay, and so now you've seen how to represent a function as a power series by integrating a power series. Now let's look at our other example where we will find a power series for a function by taking the derivative of a power series. Okay, so here's our other example. We want to find a power series for f of x is equal to 1 divided by 1 plus x quantity squared, centered at 0, and then we want to determine the interval of convergence. Okay, so remember we said at the beginning that this function has an integral that is similar to the form of the sum of a geometric series, right? We said that the integral of f of x dx is equal to -1 divided by 1 plus x. And if you don't remember how we found that, feel free to go back to the beginning of the video where I showed that integration process. And so this integral is similar to the form of the sum of a geometric series. And so remember that that form is a divided by 1 minus r. So we're pretty close. We have a constant divided by 1 and a common ratio, but we're not subtracting that common ratio like we need to be doing. And so I'm going to change this plus to be a minus by having 1 minus negative x, just like we did in our previous example. So this will be equal to -1 divided by 1 minus negative x, okay? Subtracting a negative value is the same as adding that value. And so now this is in the form of the sum of a geometric series, and so now we can represent this function as a power series. This is the integral of the function who we actually want to find a power series for. But before we can do that, we first need to write out that power series for its integral. All right, so now in this case, a is equal to -1, and the common ratio r is equal to -x. And so the power series, or the geometric power series, will be equal to the sum from n equals 0 to infinity of a, which is -1, times -x to the power of n, the common ratio to the power of n. All right, now I'm going to rewrite this from being -x to being -1 times x. So this will be equal to the sum from n equals 0 to infinity of -1 times -1 times x to the power of n. And now we can take each part to the power of n. So we'll have -1 to the power of n and then x to the power of n. And so I'll write that up here. This is equal to the sum from n equals 0 to infinity of -1 times -1 to the power of n times x to the power of n. All right, now if I clean up my work, we can simplify this power series a little further. Since we have -1 times -1 to the power of n, we can add those exponents. So we'd have -1 to the power of n plus 1. All right, so this will be equal to the sum from n equals 0 to infinity of -1 to the power of n plus 1 times x to the power of n. All right, and so this power series represents the function that is the integral of our function that we want to represent as a power series. So if we want to find a power series to represent this function, what we can do is take the derivative of this integral, right? If you take the derivative of an integral, you get back the original function. Okay, so what we're going to do is differentiate with respect to x the integral of f of x dx, and that will be equal to 1 divided by 1 plus x squared. That's our original function. And that's going to be equal to the derivative of this power series, right? This is the integral of f of x dx. So if we differentiate it, we will get a power series to represent our original function. All right, I should probably write this as well. This will be equal to f of x, which is this function right here. Okay, the derivative of an integral of f of x will just be equal to f of x. All right, so to differentiate this power series, we will multiply the exponent of x down and then subtract 1 from that exponent. So what we'll have is the sum from n equals 0 to infinity of -1 to the power of n plus 1. That's not going to change, but what will change is this x to the power of n. We will now have n times x to the power of n minus 1. We multiply the exponent down and subtract 1 from the exponent. Okay, and so this right here is the power series that represents our function f of x. Now all we have to do is determine the interval of convergence. All right, so I'll box this in. This is the power series that represents our function. And so to find the interval of convergence, we're going to do the same method we did in the previous example. We're going to find the radius and interval of convergence for the first power series we wrote out, the geometric power series that came from the function that was similar to the form of a geometric sum, right? In this case, that happened to be the function which is the integral of the function that we wanted to represent as a power series. And so we will find the interval of convergence for this series because this series will share the same radius and interval of convergence as our derivative series, except the endpoints might be different. And so because of that, we will have to go back and check the endpoints, but first, let's just find the interval of convergence for this geometric power series. All right, so I kept our value of r right here. This is our value of r for this geometric power series right here. So when the absolute value of r is less than 1, that series will converge. In this case, r is negative x, so the absolute value of r will be the absolute value of x. That negative will be removed. So we'll have the absolute value of x is less than 1, which says that when x is less than 1 but greater than negative 1, that the power series converges. All right, so we're looking at an interval of convergence from negative 1 to 1. And since the absolute value of x was less than 1, that also tells us that our radius is equal to 1. All right, so you can make a note of that if you'd like. But what we're really interested in here is the interval of convergence. We're going to test these two endpoints of negative 1 and positive 1 for this series to see if they should be included as values that make the series convergent. Okay, so if I clean up my work here, let's check our first endpoint of negative 1. When x equals negative 1, our power series will look like this. We'll have the sum from n equals 0 to infinity of negative 1 to the power of n plus 1 times n times negative 1 to the power of n minus 1. All right, all we did was replace this x with negative 1. And now we have negative 1 to the power of n plus 1 and negative 1 to the power of n minus 1. We have the same base raised to an exponent, so we can add those exponents. And if we do that, this will be equal to the sum from n equals 0 to infinity of negative 1 to the power of n plus 1 plus n minus 1, and that's multiplied by n. All right, so we added these two exponents, n plus 1 plus n minus 1, but now we have a positive 1 and a negative 1. Those are going to cancel each other out, and then we're just left with n plus n, which is going to be 2n. So what we're left with is that this is equal to the sum from n equals 0 to infinity of n times negative 1 to the power of 2n. All right, I just moved this n up front. It doesn't matter what order you multiply those two parts in. I just decided to move the n to the front because I think it looks a little bit better. Anyway, we now have negative 1 to the power of 2n, and something to note about that is that this 2 will always make this power an even power, right? Whatever value of n we plug in here, if n is odd, an odd number times 2 will be even, and if n is even, an even number times 2 is also even. So no matter the value of n, this power will always be even, and negative 1 raised to an even power will always be positive 1. So this series will just be the series from n equals 0 to infinity of n times 1. And so that will look like this. We'll have the sum from n equals 0 to infinity of n. All right, n times 1 is just going to be n. And now we have a fairly simple series that we can determine the convergence or divergence of. In this case, what we can use is the divergence test. If we just take the limit as n approaches infinity of that sequence for the series, which is just n, that limit is equal to infinity because as n approaches infinity, n approaches infinity. So the limit is equal to infinity, and from the divergence test, when the limit of your sequence for the series is not equal to 0, that series diverges. All right, so this is a pretty easy one to determine the convergence or divergence of. In this case, our series diverges, and so we will not include negative 1 in our interval of convergence. Negative 1 does not result in a series that is convergent for this power series. It is a divergent series instead. Okay, so we're going to leave that open bracket as an open bracket. We're not going to change it. Now we just have to check the other endpoint of positive 1. So if I clean up my work, when x equals positive 1, we will have the sum from n equals 0 to infinity of negative 1 to the power of n plus 1 times n times 1 to the power of n minus 1, right? We just replaced x with positive 1. And so if we simplify, 1 to the power of n minus 1 is just going to be 1, right? 1 to the power of any finite value will just be 1. So we can just completely ignore this part of the series. We can just erase that, and our series will just have negative 1 to the power of n plus 1 times n. All right, and so what we have here is an alternating series, right? Negative 1 to the power of n plus 1 is going to make the terms of this series alternate between being positive and negative. And so in this case, we can determine the convergence or divergence of our series by using the alternating series test. So we'll check both of the requirements, and if they're both met, then our series converges. So the first requirement is that the limit as n approaches infinity of the sequence from our series, excluding the part that makes it alternating, must be equal to 0. So in this case, -1 to the power of n plus 1 makes it alternating, so we're just going to pay attention to this n. Our sequence will just be n. And so the limit as n approaches infinity of n is just going to be equal to infinity, right? As n approaches infinity, n approaches infinity. And that is not equal to 0. And so from the alternating series test, or you could also say from the divergence test, this series does not converge. It diverges. All right, so this series diverges, which means that when x equals 1, our power series is not a convergent series, and so +1 should not be included in the interval of convergence. We will not change that open bracket to be a closed bracket. We're going to leave it alone. And so, -1 to 1, not including either of those endpoints, is the interval of convergence for this power series that represents this function. Okay, so that is how you can take the derivative of a power series to represent a function whose integral is similar to the sum of a geometric series. Okay, so hopefully now you can see the connection between a derivative and integral of a function and the derivative and the integral of a power series. Being able to identify a derivative or integral of a function that is similar to the form of a sum of a geometric series will allow you to create a power series to represent that function. Okay, and so with that, this is all I had for this lesson. So if you want to see some more examples, feel free to check out my examples video that I'll have linked at the end of this video, as well as in the description below. If you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.